Okay, so now we make the transition from sampling distributions to confidence intervals. So just a brief recap of what we learned about sampling distributions. The mean of the p-hats is the population p. The standard deviation of the p-hats is radical p times 1 minus p over n. And the distribution of p-hats is approximately normal if these two conditions have both been met. And remember that turning a p-hat into a z-score looks something like this. Now, some stuff we should know about any normal distribution. In any normal distribution, the z-score that corresponds to an area of 2.5% would be a z-score of negative 1.96. We can see this from the table that negative 1.96 corresponds to a left tail area of 2.5%. And this can also be illustrated on the calculator. The area from negative infinity to negative 1.96 is 0.25. So negative 1.96 is kind of an important number, as we're going to see coming up. That leaves 2.5% down in this tail. Similarly, because of the symmetry of the normal curve, the z-score that corresponds to the 97.5 percentile is positive 1.96. So z of positive 1.96 has 97.5% below it. And that's because if you have 97.5% below it, you have 2.5% above it. So if this section here is 97.5%, this little tail here is 2.5%. So that's symmetrically the same as what we had in the other tail, except instead of negative 1.96, it's positive 1.96. And here's an illustration of that on the calculator. From negative infinity to positive 1.96 is 97.5% of the normal distribution. And so if we have 2.5% below negative 1.96 and 97.5% below positive 1.96, then that means we have 95% in between the 1.96 and negative 1.96 as illustrated in this graph. So 95% of any normal distribution is going to land between a z-score of negative 1.96 and positive 1.96, which is also illustrated by this probability statement here. Okay, so if our distribution of p-hats is approximately normal, then we should have about 95% of our p-hats falling between the z-scores of negative 1.96 and positive 1.96. But the question is, what values of p-hat would give us those two z-scores? So we're going to pop those z-scores, negative 1.96 and positive 1.96, into our z-score formula for p-hat, giving us this and giving us this. And then we're going to solve both of those for p-hat. First of all, multiplying both sides by the radical, and then adding p to both sides. So therefore, saying that z is between negative 1.96 and positive 1.96 is the same thing as saying that p-hat is between p minus this expression and p plus this expression. So 95% of all values of p-hat are between p minus this expression and p plus this expression, assuming, of course, that the distribution of p-hat is approximately normal. Another way of saying that without using the word between is to say that 95% of all values of p-hat are within this far of the population proportion p. So all of this is based on what we know about the sampling distribution of p-hat from our previous chapter. And the problem with saying that 95% of all values of p-hat are within this far of the population proportion p is that we usually don't know the population proportion p. In fact, usually what we're doing in statistics is we're grabbing a sample and then we're using the proportion from our sample, which is p-hat, and we're using that as our estimate of p. when we do that, we say that p hat is a point estimate for p. However, we know that different samples will result in different values of p hat. And in fact, it's all of those different values of p hat that make up the sampling distribution of p hat. So we would like to construct an interval estimate for p to take into account our uncertainty in the point estimate, to take into account the fact that p hat will change from sample to sample. And usually an interval estimate has a format like this: p hat, which is our point estimate, plus or minus some margin of error. Or in interval form, it looks like this: p hat minus the margin of error, comma, p hat plus the margin of error. The margin of error doesn't mean, because of the word error, it doesn't mean that we've done something wrong. It just means that there's variability from one sample to another. So really it's about the sampling variability from one sample to another. So instead of saying that we think the population proportion is the value of p hat I got from my sample, we usually prefer to say, I think the population proportion is in between the p hat from my sample minus a margin of error and the p hat from my sample plus some margin of error. So now we need to transition from a statement about where p hat lies based on a no value of p to a statement about where p lies based on a value of p hat. In other words, up here we said 95% of all values of p hat are in here within this far of the population p, but now we want to say where we think p is in relation to our p hat. And if I was doing this in class, usually at this point I bring out a meter stick and I hold the meter stick between my belly and the shoulder of a student, and I make some kind of statement like, if I am within 1 meter of you, then you are within 1 meter of me. Or if let's say I ask a student to guess my weight, if their guess is within 10 pounds of my weight, then my weight is within 10 pounds of their estimate or their guess. So if 95% of all values of p hat are within this far of the population proportion p, then that means 95% of the time the population proportion p will be within this far of my value of p hat, which is exactly what I was saying up here about within 10 pounds of my weight. If the estimate is within 10 pounds of my weight, then my weight is within 10 pounds of the estimate. If p hat is within this far of p, then p will be within this far of my p hat. This suggests that up here, our margin of error should be this quantity, 1.96 times radical p times 1 minus p over n. So that would lead us to the following formula: a 95% confidence interval for the population proportion p using the sample proportion p hat would be p hat plus or minus some margin of error, and we're going to use this expression here for the margin of error. So p hat plus or minus 1.96 times that radical. So there's a couple alterations we need to make. First of all, the whole reason why we're trying to estimate the population p is because we don't know the population p. And if we don't know the population p, then we can't very well have the population p showing up in this formula. So the major modification of this formula is to replace the p with the p hat from our sample. So it's still a 95% confidence interval for the population proportion p using the sample proportion p hat, but now the formula is completely based on p hat and our sample size n. Now, this whole formula is based on being 95%. It's all based around 95% because recall at the beginning of this, the 95% mark is what determined the z-scores of positive 1.96 and negative 1.96. But in general, I might not want to be 95% confident. I might want to be 99% confident, or maybe only 90% confident. So depending on how confident I want to be, this 1.96 might take different values. So usually the confidence interval formula is written in a more generic way like this. So a confidence interval for P using P hat, still that same nomenclature, P hat plus or minus Z star times this radical P hat 1 minus P hat over N, where it's understood that the value of Z star, which in most books is referred to as a critical value, depends on the level of confidence. And here's some really common values of Z star. We see that if our confidence level is 95%, we're going to use a 1.96 right in this spot here. But if we want to be more confident, then we need a bigger value of Z. If you want to be less confident, then a smaller value of Z. So let's see how to use this formula here, the confidence interval formula, in a problem. We want to estimate the proportion of Cal Poly Pomona students that are business majors. We select a random sample of 300 Cal Poly Pomona students and find that 57 of them are business majors. Construct and interpret a 99% confidence interval for the proportion of all Cal Poly Pomona students that are business majors. So we're being asked to construct a confidence interval for the population proportion, the proportion of all Cal Poly Pomona students that are business majors, using a sample proportion P hat, which is 57 out of the 300 we sampled are business majors. So that's a P hat of 0.19. Technically, we should check conditions that we learned about in our previous chapter on sampling distributions. Do we have a random sample? Is our sample less than 1/10 of the population? And have the conditions n times p and n times 1 minus p, have those conditions been met? Notice that I'm using P hat here instead of P because I don't know the population P. I'm estimating the population P. So technically, all of those conditions should be met before we dive into the calculations for our confidence interval. But oftentimes in the introductory class, those conditions aren't checked, but they should all have been met to make our confidence interval valid. So all we need for our confidence interval formula is the sample proportion P hat and our sample size, and our critical value 2.576 from this table up here. When the confidence level is 99%, they said make a 99% confidence interval. When the confidence level is 99%, the Z star we should use is 2.576. So 2.576 there, our P hat of 0.19, our P hat of 0.19, 1 minus our P hat of 0.19, and our sample size, which is 300. Usually I do this whole calculation here after the plus or minus sign because that quantity there is our margin of error, 0.0583. So 2.576 times a radical 0.19 parentheses 1 minus 0.19 close parentheses divided by 300. So there's our margin of error of 0.58. And sometimes it's left in this form with this plus or minus, but oftentimes it's written in interval form. So you do the 0.19 minus the margin of error and the 0.19 plus the margin of error, and that gives you these two numbers here. Students often get these two numbers backwards because when we see this sign, we say plus or minus sign, but we're actually doing the minus part of it first. So 0.19 minus the 0.05 gives us the low end of the confidence interval, and 0.19 plus the margin of error gives us the upper end of the confidence interval. This calculation can also be done on our graphing calculator. So on the Stat button, under the Tests menu, there is a test called a one proportion Z interval. And we start off by entering the two numbers that make up our P hat, that is 57 people out of the 300 we sampled are business majors, and we enter our confidence level, which is we're doing a 99% confidence interval, but we have to enter the confidence level as a decimal. And so there's 0.13 and 0.24, which is exactly what we got here, which is exactly what we got up here, 0.13 and 0.24. Now, in this example, the sample proportion came out to be a nice looking number. Oftentimes, when you do this division, you get a long, ugly looking decimal. If that happens, I suggest keeping this decimal answer to 4 or 5 decimal places. I usually do 5 decimal places, but I would say 4 at minimum. Okay, a couple other loose ends, I guess, to tie up. In many classes, interpreting the confidence interval is as important as constructing the confidence interval. And the reason for that is we often have some kind of technology that will spit out the confidence interval for us. So once we have that confidence interval calculated, whether we calculated it or some technology gave it to us, interpretation is often a big deal. So in general, the interpretation goes like this. I am blah % confident that the population parameter is between A and B. In our particular case, the population parameter is the proportion of all Cal Poly Pomona students that are business majors. So our interpretation of this confidence interval would go like this. I'm 99% confident that the proportion of all Cal Poly Pomona students that are business majors and the proportion of all Cal Poly Pomona students that are business majors, that phrase right there is our population parameter, our population proportion P. I'm 99% confident that P is between 0.13 and 0.24. So I'm 99% confident that the proportion of all Cal Poly Pomona students that are business majors is between 0.23 and 0.13 and 0.24. Sometimes when it's written out like this in words, you would change those decimal numbers to percentages, 13% and 25%. That's not necessary, but that's sometimes done. And also, this word all here is kind of important because this interpretation should be an interpretation of where I believe the population proportion P is based on the endpoints of this interval that I just created. I'm 99% confident that the population proportion of all Cal Poly Pomona students who are business majors is somewhere in this interval. Okay, additional point number 2. Sometimes you are asked to interpret the confidence level, and as you can imagine, interpreting the confidence level often gets confused with interpreting the confidence interval. Interpreting the confidence level is really trying to get a handle on what does it mean when you say you're 99% confident. When you say you're 99% confident, that means that 99% of the time, this confidence interval I created will contain the actual population P. I'm not sure if this particular interval contains the population P, but I know if I did this over and over again, 99% of the confidence intervals I create will capture the population P. So when I construct a confidence interval like this, 99% of the time, the population proportion P will be in our interval. Or sometimes people get a little bit more wordy and say, we're constructing a confidence interval using a procedure that creates confidence intervals that capture the population proportion 99% of the time. This interpretation is a generic interpretation of what it means to be 99% confident. Notice I'm not saying anything about the particular confidence interval that I created up here, just about what it means to be confident in general. Let me show you a picture of what it means to be confident in general. So here's this app that will create confidence intervals. So I'm going to pretend that the population P is 0.2, and I'm doing a confidence level of 99%, and the app won't let me do a sample size of 300, so I'm going to do a sample size of 250. So I click on sample, and hopefully I see something happen. I click on sample. Here's my p hat of 0.17. and plus or minus a margin of error of 0.06, which is kind of like our margin of error. And so when I subtract 0.06 and I add 0.06 to the p-hat of 0.17, notice that this confidence interval contains the population p of 0.2. Now, this confidence interval does not contain the population p of 0.2. This time our sample resulted in a p-hat of 0.13, and when we went plus or minus 0.06, this confidence interval did not contain the population p. But most of the time that does not happen. Most of the time you're going to get a p-hat that's relatively close to the population p, and so therefore when you go minus the margin of error and plus the margin of error from that p-hat, this interval contains the population p. Most of the time, the confidence interval you create will contain the population p. And when I say most of the time, this should be happening 99% of the time if we're doing a 99% confidence interval. Now there I just did another 25 at a time. There's another 25 confidence intervals. And there's another 25 confidence intervals. So I've so far created 100 confidence intervals, and 99 of them contained the population proportion, which is 0.2. Every once in a while, just by chance, you're going to get a goofy value for p-hat, and then the confidence interval based on that particular value of p-hat does not contain the population p. But that doesn't happen very often because p-hats like this don't happen very often. So this is kind of what an illustration of what it means to say that we're 99% confident. One other final point to wrap this up is sometimes we are asked to do a sample size calculation. So, for example, in our problem, we had a margin of error that was almost 6%, plus or minus 6% roughly. What if you don't want to have a margin of error that big? What if you only want to have a margin of error of 3%? What sample size would be required to have a margin of error of only 3%? So the entire expression after the plus or minus sign is our margin of error. What we need to do is we need to replace 300 with n, and we need to make this whole expression equal to our margin of error, 3%, and then solve for n. So we want the margin of error, which is our z-score, and then the radical p-hat, 1 minus p-hat over n. We want that to be 3%. Notice I changed the 3% to a decimal. So now we got some solving to do. Divide both sides by 2.576. Then I'm going to square both sides to get rid of the square root sign. Then I'm going to take the reciprocal of both sides. And then I'm going to multiply both sides by 0.19 and multiply both sides by 1 minus 0.19. And after doing all that, we get n equals 1135. So we need a sample size of 1100 to have a margin of error of 3%, instead of our original sample size, which you'll recall was only 300. So we need to almost quadruple our sample size to get the margin of error down to 3%. I left this written like this so that we could transform it into symbols. So the 2.576 is our z star, the 0.03 is our desired margin of error, and this is our p, and this is 1 minus p. So this formula for desired sample size is often written in one of these two formats. Sometimes we realize after constructing the confidence interval that our margin of error is too large, and we try to figure out, like we just did up here, we try to figure out how big of a sample should we have gotten. But it's actually better practice if the statistician figures out ahead of time what's an acceptable margin of error, and based on the acceptable margin of error, they determine ahead of time what sample size they should get. The problem is, if we haven't done a sample at all yet, then how do we know what value of P to put in this formula? It turns out that the worst case scenario is to use a value of P of 0.5. So if you have no previous knowledge what P is, you should plug P equals 0.5 into the sample size formula. Let me show you an illustration of that. So remember, this is the formula for sample size, n equals this. I have that exact expression in Desmos, except instead of n equals this, I have f of x equals this. Instead of p and 1 minus p, I have x and 1 minus x, so it's a function of x. And this turns out to be an upside down parabola. And this upside down parabola always has its maximum at a value of p 0.5. If I change what I want the margin of error to be, that will change the shape of the parabola, but the peak of the parabola, the maximum sample size I would ever need, still occurs at a p of 0.5. I can also change my value of z. Instead of 1.282, I could have a bigger z. And that changes the height of the parabola, but it does not change that the peak happens at a value of p of 0.5. So worst case scenario is if you don't know what p is, plug in 0.5 in place of p and use that. So that's how we do problems when we're doing a confidence interval for a population proportion. Make sure you watch the next video, which is constructing a confidence interval for the population mean.